Hello everyone, welcome to our discovery of our third conic section. Now what I'd like to say is before I continue is if you want to discover this conic on your own without me walking you through it, go ahead and pause the video and check out a link to this Desmos animation in the descriptions. You can also find a link to this animation in our wall map page, and I've hopefully given you some good guided directions on how to use this animation. But if you do decide to pause the video and discover this on your own, make sure you come back to the video because at the very end we are going to derive a formula for this shape on the whiteboard. Okay, so let's get started. So our very first conic we defined from a dot and a fixed distance. We thought about all the points that are a fixed distance from a single point, and we got our beautiful circle. Our second conic we derived from a single point called the focus and a line called the directrix, and we thought about the set of points that are equidistant from the focus and the directrix, and we got our beautiful parabola. For this conic, we're going to define our shape not from one dot or from a dot and a line, but from two dots. Two dots and a fixed length, which we'll call a string. So while I'm saying string here, is what I used to like to do when I would teach this in class is give students pieces of paper. I would give students these kind of clips that you could put into your paper. I would let them cut this string, and with these two dots and a string and a pencil, you can draw this shape. And I highly recommend if you have the, all the resources at home, you could draw a bunch of these shapes at home on pieces of paper. Okay, so let's do it. So we have these two dots, which we are going to call foci. It's plural for focus. And we're going to have a string. It's going to be a string, and it's going to be of a fixed length. Okay, so now for convenience, really just for convenience of measurement, we are going to lie the foci along the x-axis, and we're going to put the origin in the center of the foci. So to see them, you can click on this folder right here. You can open it up. So here are our two foci. Okay, and we want to be able to change the distance between these foci. I mean, at home you could punch these two clips into your paper anywhere you'd like. Here in this animation, we want to control how far they are apart. So we're going to define this parameter called c, and c will be the distance from the origin to one of the foci. So to see this distance, I'll open this folder right here. So we have this blue length. This is from the origin to one of the foci. So since the origin is halfway in between the two foci, the distance from the origin to the right foci will be c, and the distance from the origin to the left foci will also be c. So the distance between the two foci will be 2c. Okay, and we can use the slider right here to change how far they are apart. Okay, so you choose where to punch your foci or these two clips into your paper. Okay, then what we're going to do is we're going to cut our string. We're going to cut this piece of string, so that's what I have right here. You can click on this. So here's the string that we've cut, and we can choose how long we want the string to be. So you can change, I'll explain, you'll kind of see why here in a second. This is moving up and down, but you can choose how long you want the string to be. So you can have it short. You can see it's kind of changing this distance to the foci right now. And the reason is because what we're going to do with this string once you cut it is we're going to tie each of the ends of the string to one of the foci. So if you have to be able to tie the string to the foci, you can't cut your string too short. The length of the string can't be any smaller than 2c. So actually notice here, if you look at how I've defined c is going to go from 0 to the length of the string divided by 2. So here is the length of the string. So if we cut that in half, c can only go out to the length of the string divided by 2. So that means that puts kind of a restriction on how far part C that just puts a restriction on how far C can be apart from one another. Okay, So you can pick our string length. And now what we're going to do is we're going to tie these strings to each of these foci, and we're going to take a pencil and we're going to kind of pull this string taut along the y-axis. So for right now, let's get rid of C. Okay, so what are we doing here? The string will act as a guide for our pencil, and so we're going to imagine putting a pencil under the string and pulling it taut along the y-axis. So if we turn on this folder here, that'll get our pencils ready. So here we go. We've taken the string, we've tied it to the two ends, and we've pulled the string taut with our pencil. It actually turns out our pencil will be a green pencil. And now this string will act as a guide, and what we're going to do is we're going to rotate our pencil. We're going to rotate our pencil counterclockwise around these two dots, keeping the string taut, and we'll see what kind of shape we'll make. So this N here is going to control our pencil. So let's check it out. What's going to happen? So here we go. We're moving our pencil around, keeping the string nice and taut. And so right here, if you were doing this at home, you kind of have to pause and you'd have to kind of pick up your pencil. You'd have to pick up your pencil and you'd have to move it a little bit and then, put your pencil right back in between the two strings here. But since we have this nice animation, we don't have to do that. So we'll just keep moving the pencil around, and here we get our conic. This is our third conic. Okay, maybe to show it a little bit better, let's actually change how far our foci are apart. Let's move them a little bit further apart. Let's move them further apart. And let's draw our shape. So here we go. And what we're getting here looks a lot like an elongated circle. We call this shape an ellipse. Now notice something really quick. If I take the C here, the distance between the two foci, if I actually make the distance 0, that puts both foci at the origin, you can actually see why the string is moving up and down. Now I kind of have it programmed so the string always lies above our ellipse at a certain distance. So that's why it's moving. So if we move our foci together, and we have just a single foci and a fixed length, and we were to move our pencil around, well, we would just have a circle. But now if we don't just have one foci, we have two foci and a string attached to them. Now we're going to get this elongated circle, which we call an ellipse. Now notice, I guess a thing to think about here is really this ellipse is defined really by two different parameters. The shape of the ellipse depends how far the foci are apart. So we can go up here, and I recommend you playing around with the distance the foci are apart and the length of your string. But if the foci are further apart and you keep the string the same length, the further they are apart, the more elongated your ellipse will be. Okay, and then if it's if your foci are a distance of the length of the string divided by 2 apart, well, you're really not going to have anywhere for your pencil to move. You'll be able to just move it, back and forth and make this line. But if the string is fixed and the foci are further apart, the ellipse becomes more elongated. If you bring them closer together, you get an ellipse that's much more circly. It's much more circly. They're further apart, and you get a much more ovally or ellipsy kind of shape. Okay, but that's not the only thing that would change. Well, if we have a fixed foci, you could also change the length of the string. So if the string is longer, and you have a fixed foci, you'll have something that'll be a little bit more circly if you increase the string length. But if you decrease your string length here, and have a fixed distance on your foci, you'll get a more elongated ellipse. So it really depends on two things: how far apart your foci are apart and the length of your string. Pretty cool. This is our third conic section that we've discovered so far. So now what I would like us to do is we would like to think now about a geometrical definition of this ellipse. So we came up with geometrical definitions for the other two shapes. What is the geometric definition of a circle? The geometric definition of circle is the set of all points that are a fixed distance from a point that we call the center. What was the geometrical definition of a parabola? The definition of a parabola was the set of all points that were equidistant from a point called the focus and a line called the directrix. Well, what is the geometrical definition of the ellipse? What I would actually like you to do is I want you to pause the video right here, and I want you to try to think about what should the geometrical definition of an ellipse be. Maybe thinking about the length of the string and how this shape was drawn. So pause the video and try to write down a geometrical definition of the ellipse on your own before we go over it together. Okay, so if you open up this folder, I've kind of guided us through the answer. So what is the answer? Well, the key thing to observe is that for a fixed, if you fix the foci, but the key thing is you're going to fix the length of the string, and that is the most important part. Whenever you're drawing this ellipse, there's one string and its length is fixed. So the whole time we're moving around the circle, the length of the string here never changes. So that should now tell us a little bit of information about points on this ellipse. Well, if we think about a point on the ellipse and we think about the distance from that point on the ellipse to this foci, and then think about the distance on the from the point on the ellipse to the second foci, well, the sum of these two distances has to be constant. It always has to be the length of the string. It never changes. Pretty much that is the definition. Really, the set of all points on the ellipse, the definition would be that the distance from the sum of the distances from a point on the ellipse to two foci, those two distances will always sum to be the same, will always sum to be a constant. They'll always be the length of the string. To see this a little bit better, I've color-coded the strings, or I've broken the string up into a couple different pieces, so let's move it up here. So let's color code the string. So what I have here is that the part of the string that goes from the left foci to your pencil will be red, and from your pencil to the right foci will be purple. And as we can actually see the string distribution. So this black line here is the length of your entire string. Okay, this red part is the distance from this left foci to the point on the ellipse, and this purple piece right here is the distance from the point on the ellipse to the right foci. And as we move our pencil around, let's go up here. As we move our pencil around, these lengths will change. But notice that the sum of these lengths will always add up to the length of the string. They'll always add up to the length of the string. So the definition of a parabola, or I guess I have it written right here, a parabola, the definition of an ellipse is the set of points such that the sum of the distances from two foci are constant. Or less formally, red string plus purple string equals black string no matter where our pencil is. Sweet. So there we have it. The formal definition of an ellipse really comes down to just making the observation that no matter where our pencil is when we draw this, the string length changes the same, which just means that if we have a point on the ellipse, the sum of the distances from that point to the two foci will always be the same. They'll always be the length of that string. Now, let's go ahead and use this geometrical definition of the ellipse. Let's go to the whiteboard and see if we can derive a formula for it. We'll see you there. Okay, so we just discovered the geometrical definition of an ellipse. An ellipse is the set of all points in the plane such that the distance from two foci, the sum of the distance from two foci to that point, will be constant. What we want to do now is let's go ahead and draw a picture and see if we can come up with a formula for the ellipse. It's going to take a little bit of board space. We'll see what we can do with this. We'll get it done. All right, let's draw the ellipse and let's label a few things. Okay, finding the equation of the ellipse. Okay, so let's draw an ellipse. Okay, not perfect. It's not perfect, but it's enough. It's enough to get an idea of what we want to draw here. Maybe I can do a little bit better. Do a little bit better. Try to make it as symmetric as possible. Oh, there we go. Okay. So we have two foci. Here's one. Here's another one. Okay, and in the video, remember that we said that the distance from the origin to a foci, this distance here is c, which means that this distance here is also c. So let's write the coordinates of these two foci. So for this foci right here, it'll have an x-coordinate of c and a y-coordinate of 0. Since we're to the left of the origin, we'll have the coordinates here will be negative c and 0. So those are the coordinates of those two spots. Okay, just so our picture isn't too I guess crowded, let's erase these c's here. Okay. Now there are some other measurements. There are some other measurements that we write on an ellipse. You can kind of think of an ellipse as kind of almost having two different radiuses. A circle just has one radius because the distance is fixed when you move around. An ellipse kind of has two radiuses. It has the longer radius, kind of the biggest radius, and the shortest possible radius, this one here. We call this is called the length of this would be like the semi-major axis. We'll talk about more of that in the next video. But what I just want to say here is we define the length from here to here, this kind of longer radius, we denote that with an A. Okay, so this distance here is A, which means that this distance here will also be A. The shape is symmetric. And kind of the shorter radius, we'll actually call this the minor axis. We'll call this the semi-minor axis. But for right now, this kind of shorter radius, we denote with a B. And this will also be the same shorter radius, which we'll also call B. Okay, I'm going to erase a little bit of this because, again, we don't want our picture to get too clogged up. Let's actually mark a few points here. So we'll actually know the coordinates here and here. The coordinates here, it'll have an x-coordinate of A and a y-coordinate of 0. Here we'll have, since we're to the left of the origin, we'll have an x-coordinate of negative A and a y-coordinate of 0. Okay, right here we'll have a x-coordinate of 0 and a y-coordinate of B. And right here we'll have a x-coordinate of 0 and a y-coordinate of negative B. So we'll mark those and kind of erase a little bit of this picture here. Just leave lines. You'll see that we're just going to need a little bit of space. Okay. Now what we're going to do is let's go ahead and grab a point on our ellipse. So let's grab a point right here. It doesn't matter where you put the point. I'm going to put it right here. So here we have a point X and Y. X and Y. And what must we know that's true about this point based on the definition? Well, if we draw a line from I guess maybe we'll call this the first foci, or from the left foci, from here to here. Okay, let's call this distance 1. We'll call it, how about D1? And then we have the distance from our right foci to our point. How about we call this here distance, we'll call this one here distance 2. Distance 2. Okay, I'm going to make that 2 a little bit better. Or distance 2. Okay? Now, what must we know? What is the definition? What is the definition of an ellipse, well, we have that the sum of these two distances must be a constant. We have d1 plus d2 is equal to a constant. Okay, well, what is this constant? Well, this is just kind of like the length of the string that you would have cut to make this shape. You can kind of think of this as the length of the string. Okay. So let's go ahead and actually try to write down what these two distances will be here. Okay, so we're, of course, going to be using the Pythagorean theorem again, so let's draw some right triangles. Let's do it. Okay, let's grab a red marker. Ooh, and a purple one. See if that one works. Okay, let's think about D1 here first. So let's think about this right triangle right here. This right triangle right here. Okay, so what we want to do for this right triangle, maybe I'll draw it right here. Okay, this is D1. Okay, now we just need to figure out the length of the lengths of the legs. Okay, well, let's kind of draw this over here. Since this point here has an x-coordinate of x and a y-coordinate of y, that means this here will be y, and right here will be x. So I think right off the bat, hopefully what we can see is that the length of this, I guess the vertical leg will have a length of y. So this vertical length here, this vertical leg will have a length of y. Okay, and what will be the length of the horizontal leg? Well, notice that the length from here to here, this physical length, is c. From here to here has a physical length of c. But then from here to here, from 0 to here, this has a length of x. So this physical length here must be c plus x. C plus x. Okay. Well, we'll do the Pythagorean theorem here in just a moment, but we have the other triangle we need to look at. Okay. Let's look at this other triangle to figure out distance d1. Let's see if my purple marker works. Let's hope. Purple's fun. Okay, so we have this smaller right triangle right here. So let's sketch this one. Okay, so this here is D2. Okay, again, the length of the vertical leg here will still be y. Okay, and now what is going to be the length? What is going to be the length of the horizontal leg? Well, hopefully what we can see is, well, the distance from here to here, I just erase it, but this length here is x, and the length from here to here is c. So this is the length that we want. To get that length, we could take the length of x and remove c. So this length here will be x minus c. Beautiful. Okay, now let's just use the Pythagorean theorem. Let's use the Pythagorean theorem. Okay, so d1, this distance squared is equal to the distance, the square of the hypotenuse is equal to the sum of the square of the legs, or we could say that d1 will be equal to the square root of y squared plus ac plus x squared, okay, plus d2 here, that'll be the square root of y squared plus an x minus c squared. So we have d1, I have d1 right here. This is d1, maybe I'll write that in red. This is distance d1. And this here is distance d2. And this must all be equal to, a constant. Okay, that's what we have so far. Okay, what we want to do now What we want to do now is let's try to think about what the constant here should be. We're actually going to play around with this formula to get a little bit more information about it. This will actually help us when we want to clean up this formula. I mean, what can we really do to clean up this formula if we don't know what the constant is? To make this nicer, we would like to kind of like square both sides to kind of get rid of these square roots, but we have to figure out what this constant is. What is the length of the string? Let's figure that out. I'm going to erase a little bit of this here. Okay. So what we're going to do here is let's actually pick some convenient locations on our ellipse. Let me redraw it so we have a kind of a fresh ellipse to look at. Okay, let's take a look. Let's take a look at some locations. Okay. So we have from here to here is C. Okay, from here to here, from here to here is also C. Maybe in some different colors. From here to here, for right now we'll just say, well, we'll do it all. This is A. This length here is A. The length from here to here is B. And the length from here to here is B. Okay, let's go ahead and choose a convenient location. A convenient location to choose is, let's actually put the string right here. So we have our pencil, wherever we want to rotate it, let's say we have our pencil right here. Okay, so we would be at the location. What would be the x and y coordinates here? Well, it would be A and 0. This would be the x and y coordinates here. Okay, what would be the length of the string, which is really just what the constant is? Remember, the constant is the length of string. Okay, well, if we put it here, I mean, maybe we could just look at the picture. So where would the string start? The string is going to start here. Maybe I'll draw it up above. The string is going to start here. It's going to go all the way out to here. And then it's going to curve back to the focus right here. Let's try to think about what this string here would be. Maybe you could pause the video and think about it on your own. What would be the length of that string? Well, let's kind of notice something. The length of the string, we go from here and we go all the way out, but then we kind of come back. Notice here that the distance from here to here is kind of repeated. We run past this distance and then we come back. If we were to take this portion of the string, imagine taking a piece of a set of scissors, cutting it right here. Take this piece here, since the shape is symmetric, I could put it right here. I could put that piece right here. So what I have displayed from here to here, remember we cut this lower part off and we line it up, well, the length of the string would fit along the entire, what we call the semi-major, or what we call the major axis. So the length of the string must be 2A. The length of the string must be 2A. It must be 2A. It must be 2A. That's the length of the string. Okay, maybe if you don't like the argument, this formula here should tell us that too. This formula here should tell us that. Let's replace the x's with a's and the y's with zeros. So what would we get here? We'd get the square root. Well, we get a 0 squared plus, what are we going to get? We're going to get a c. What is our x? Our x is a squared. Okay, plus, we're saying our y is 0. We still have that square root. So we'll have a 0 squared plus our x is 0. So we'll have a 0 minus c squared. I meant to put our x. Yeah, our x is a. Everything's good here. Oh, sorry. Our x is a. Our x is a. Okay, and that's got to be equal to the constant. Okay, so what happens here? Well, this is 0. So what do we have? We have c plus a quantity squared, all square rooted, plus the square root of a minus c squared. Okay, well, this is going to be equal to the constant. Well, these square roots get rid of the squares, so we just get c plus a plus A minus C would be equal to the constant. Okay, well, the C's cancel each other out, and we get that 2A is equal to the constant. Don't you just love when math works? So you could have either just kind of tried to figure out what the length of the string is going to be. Remember, the length of the string doesn't change. We could see from this nice location we put our pencil that the length of the string must be 2A, but the formula we derived told us that that constant or the length of the string must also be 2A. Cool. Okay, let's hold on to that. So now we can do a little bit more. We kind of cleaned up this formula a little bit. Okay, so this constant is going to be the same thing as 2A. Okay, well that's nice so far. Well, that's nice. Okay, so we have a little bit more here. Okay, now there's one other convenient location that will actually give us a beautiful relationship between the A's, the B's, and the C's. Okay, another great location is to not choose this point here. I guess another nice location, instead of picking this point to put your pencil, you could have put your pencil over on the other side and made the same argument. Maybe it's a good exercise for you to do on your own. But another good location to put our pencil is right here. So let me draw the ellipse again. And this location is nice to remember because it does give us a good relationship between the A, B's, and C's, which will be really helpful for us when we start working with the formula. Okay, so we're going to put our string right here. So this is where our pencil is when we'd be drawing it. Okay, let's remember a few things here. How did I color code them? Looks like this here is C. Okay, maybe I'll just label that one. This one here would also be C. And in green, well, this must be B. Okay, I want you to pause the video and think for a second, what should be the length? What should be this length right here? Okay, well, I'm going to argue that the length right here is A. Why? Why is this A? Well, my picture's not perfectly drawn, but if you do put your pencil right here, since these two foci are an equal distance apart from the origin, if you put your pencil right here, the length of this line and the length of this line should be the same. Just at this location, I guess at this location too, but right here, these two lines will have the same length. And we just discovered that the length of the line, or the length of the string, was 2A. So this is half the string, so this length here must be A. It must be A. I hope that made sense. So what's great about this is what? Look at this another beautiful right triangle. Oh man, this ellipse is too good to us. Check that out. We have a Pythagorean theorem relationship between the A's, the B's, and the C's. What this is telling us, and we're going to hold on to this because this is going to be useful, what must be true, make sure we're not in that glare, okay? What must be true here, based on this location where we put our pencil, is that A squared must be equal to B squared plus C squared. Okay, this is just the Pythagorean theorem. Now, a lot of times when students see the Pythagorean theorem, they're used to the hypotenuse being labeled C. Here, we're just labeling the hypotenuse A. Don't get confused that the C is over here. I'm just choosing different letters to represent different sides. For our picture here, A is the hypotenuse. So the square of the hypotenuse is equal to the sum of the square of the legs. So we have A squared is equal to B squared plus C squared. If you ever forget this is something we're always going to be coming back to, this A squared is equal to B squared plus C squared. I highly recommend just drawing this picture. This is what I always do. Okay, with these pieces, now we're finally ready to do some hairy algebra. Okay, maybe this is the good time to pause the video. Go drink some coffee. Maybe I should go drink some coffee. We're gonna have some hairy algebra here. Okay, let me write this formula up. Maybe I'll take a sip of coffee, and then we'll get into some deep concentration on cleaning this formula up. Okay, so this is what we have. We have the square root of y squared plus a c plus x squared. Okay, what plus the square root of y squared plus a x minus c squared is equal to 2a. And what we're going to hold on to, shouldn't have erased it, what we're going to hold on to is that we know that a squared should be equal to b squared plus c squared. Okay. Okay. Ooh. Ooh. Gonna need a little bit of concentration here. All right. How are we going to clean this thing up? What are we going to do here? Well, the key thing that we need to do here is we need to start cleaning up. We got to get rid of these square roots. So the first thing I'm going to do is we're going to start squaring both sides. We could square right off the bat, but what I'm actually going to do is I'm going to move this piece to the right-hand side. So we're going to get the square root of y squared plus a c plus x squared, and that's going to be equal to a 2a minus the square root of y squared plus a x minus c squared. Okay, what are we going to do from here? Is we're going to square both sides. We're going to try to get rid of one set. We're going to try to get rid of one set of these square roots. Okay, so this is all we're just trying to massage this, we're trying to massage this into something prettier. Okay, so we got to square both sides. Okay, well, this square root will get removed. So we'll be left with a y squared plus a c plus x squared. The square root goes away. And now, unfortunately, what do we got to do? We need to expand this. Okay, so what are we going to get? Well, we're going to get a 2a times a 2a, so we'll get a 4a squared. And then we're going to get a minus 2a times this quantity, but we're going to get two of those. So we'll actually get a minus a 4a times the square root of y squared plus x minus c squared. This just comes from the o and the I in FOIL. They're like terms, and I'm adding them together. Okay, then I'm going to get, this is going to be the L in the FOIL. I need to square this piece. So we're just going to get a plus. This piece will be squared. We're going to get the y squared plus the x minus c squared. So that's what happens when we square the right-hand side. Okay, really just foiling. Just, this is just intense foiling. We're just putting our foiling hats on. Well, what's great so far? What do we notice? Things are already canceling. Look, we can subtract y squareds from both sides. Well, that's convenient. We can subtract those y squareds from both sides. Okay, well, what else can we do here? How else can we clean this up? Well, I mean, eventually we're going to need to square again to get rid of this square root piece right here. But all of these pieces right here, this c plus x quantity squared and this x minus c quantity squared, if we were to actually FOIL these pieces out, I think more things are going to cancel. So let's keep our foiling hat on and let's expand. Okay, so this right here, if we expand it, we'll get a c squared plus a 2cx plus an x squared. That'll be equal to a 4a squared minus a 4a times the square root. We'll have a y squared plus a x minus c squared plus here, we'll get an x squared. We're going to get a minus a 2xc plus a c squared when we expand the x minus c quantity squared. Okay. Well, let's make sure, let's see if I can get a little bit better of a marker. Running low on markers. Make this show up a little bit better. Okay. So what's great is, subtract c squared from both sides. Subtract x squared from both sides. Look at this canceling. It's great. Okay, what else are we going to notice here? Well, we have a negative 2xc here. We have a positive 2xc here. Just change the order of multiplication. But let's all move those to one side. Let's move those to one side. Let's go ahead and add this piece to both sides. So let's add 2xc to both sides. So 2xc is the same as 2cx. So what we're going to get here is we're going to get a, what are we going to get? We're going to get now a 4xc, okay, will be equal to a 4a squared minus a 4a times the square root of y squared plus an x minus c squared. Okay, whew. Okay, we want to isolate this piece here. We want to isolate this piece so that we can square both sides. So I'm going to go ahead, well, I guess one thing to notice that we can do is we could divide everything by 4. If we divide everything by 4, well, these 4's will cancel. You could factor a 4 out of these parentheses and cancel it out. For the sake of me saving some board space, we can just divide out these 4's. You can divide out these 4's. And what I'm going to do is I'm going to isolate this piece, so I'm going to subtract a squared from both sides. So we'll get a xc, an xc minus an a squared is going to be equal to a negative a times the square root of y squared plus x minus c squared. Okay. So you could divide both sides by negative a from here if you would like, but we really just want to get rid of the square root. So what are we going to do? We're going to square both sides again. We're going to square both sides again. Okay. And because we're running low on space, I'm going to kind of maybe move this up. Okay. Whew! I think I drank that coffee. Okay, we're not done yet. But we're getting somewhere. Okay. Let's see. So let's go ahead and FOIL out the left-hand side. So if we FOIL out the left-hand side, maybe this one I will write out just so I don't make a mistake. xc minus a squared times an xc minus an a squared. Let's expand this. So we'll get an xc times an xc. We're going to get an x squared c squared, an x squared c squared, an x squared c squared, and then we're going to get a minus xc a squared, an xc a squared, but we're going to get 2 of those from the O and I in FOIL, so we'll have 2 of these. And then we'll get a negative a squared times a negative a squared. We're going to get plus an a to the 4th. Okay, and that's going to be equal to, what happens when we square this? Well, squares distribute through multiplication, so we'll get a negative a squared, or just an a squared, times this square will hit the square root, and that'll cancel. So we'll just be left with the y squared plus the y squared plus, we have this x minus c quantity squared. So that's when I squared the square root. The square root goes away, and I squared the negative a, so we're just left with a positive a squared. Okay. So we are getting somewhere. We're getting somewhere. Okay, what do we want to do now? Let's erase some of this. Okay. What we're going to do now is we're hoping some more pieces cancel out, so we're also going to expand this x minus c quantity squared. Okay, so what are we going to get? Okay, keeping our foiling hats on. We're going to get an a squared, we'll get a y squared, plus, what are we going to get here? We're going to get an x squared minus a 2xc plus a c squared when I expand this piece here. And we're going to distribute that a squared in, so we're going to get a squared y squared plus a squared x squared minus a what? A 2xc a squared plus an a squared c squared. All I'm doing is distributing this a squared into these parentheses. And on the left-hand side, we have the x squared c squared minus a 2xc a squared plus a to the fourth. Woo! All right, well, can we cancel anything? Can we cancel anything? Well, let's see. Well, we have a negative 2xc squared. A negative 2xc squared. Add that to both sides. These will go away. Awesome. Yes. Okay, we have an x squared c squared plus an a to the fourth is equal to an a squared y squared plus an a squared x squared plus an a squared c squared. Okay. So what to do from here? Well, it's going to be convenient for us to group some terms, especially together. Mainly, we're kind of thinking about this a squared is equal to b squared plus c squared. There's no b's here, and we're kind of hoping to get that b piece to show up. So over here, we would note that a squared minus c squared would be equal to b squared. So it'd be kind of nice to get kind of like an a squared minus c squared piece to show up. So this, again, if you were doing this for the very first time, this might just kind of take some kind of trial and error. But it turns out that if you, let's see, what pieces do we want to move? We're going to keep this piece. We're going to keep this piece on the left-hand side, and we're also going to keep this piece here. We're going to move this piece here to the left-hand side, and all of the other pieces we are going to have on the right-hand side. So we're going to get a to the fourth. I'm going to subtract this piece to the other side, so minus an a squared c squared. Okay, and that'll be equal to, we'll have the a squared y squared plus the a squared x squared, and then minus an x squared c squared. Okay, well, what's nice here is we can factor out an a squared. So if we factor out the a squared, we'll be left with what? We'll be left with an a squared minus a c squared, which is nice because we're going to change that into a b squared here in a moment. Okay, and then over here, well, let's see. Well, we have this a squared y squared, but over here, I think we want to factor out an x squared because we're going to get another a squared minus c squared. So if I factor an x squared out of these pieces, an x squared, this now is just like clever massaging, trying to group pieces nicely together to kind of get a b squared in there somehow. Okay, so then we'll get what? An a squared minus c squared. Man, we are almost there, I promise. Okay, this is the same thing as b squared. So now we have a squared times b squared is going to be equal to a squared y squared plus, now it'll be x squared times a b squared. Okay, last step that we're going to do, just to kind of give you the form that you oftentimes see in ellipsin, is we're going to divide everything by a squared times b squared. So we're just really dividing both sides by a squared times b squared. And where does this get us? Okay, so we have now that 1 is going to be equal to, well, the a squareds cancel, and we're left with what? We're left with y squared all over b squared plus what? These b squareds cancel. We get out a x squared over a squared, or how about I write 1 is equal to x squared over a squared plus y squared over b squared. And here we have it. This is the equation. Of an ellipse. This is the equation of an ellipse. Beautiful. Okay. Took us a lot of work, but man, look look how pretty this formula is compared to what we had before. It took some clever massaging, but we got there. We got there. Let's think about this formula here for a second. This is how I like to think about it. I'll give you two great ways to think about this formula. Okay, let's draw the ellipse here really quick. Let's draw the ellipse. What's great about this formula? What's great about this formula? Okay, here's our two different foci. Here's our two different foci. Well, this here is what, B, and this here is A. Well, what happens if we had our foci, or in this case here, what if this distance C here, what if this distance C here was 0? Well, if C was 0, for example, if we look up here, if C is 0, we're going to get that A squared will be equal to B squared. If C is 0, that means I'm basically taking these 2 points and I'm bringing them to the origin, so we only have one focus now. Well, this is basically saying that A would be equal to B. So the A and B will be the same. So this radius and this radius will be the same. What shape is that? That's just going to be a circle. So let's say the A and the B will be the same. Well, let's call that one common length R. So that should give us now a circle. Well, what happens if we replace A and B with R? We're going to get a 1 equals x squared. Well, if A is R and B is R, and now multiply both sides by r squared. Well, when this distributes in, what are we going to get? We're just going to get that r squared is equal to x squared plus y squared. That's the equation of a circle. And that's the equation of a circle. How beautiful is this? Think about all the algebra we just did and how crazy that algebra was. And it all just came down to us getting this formula. But then when we just said, hey, what happens if A and B are the same and they're both R and we should get a circle? Well, the ellipse equation just turns into the equation for a circle. Beautiful. Okay, what is another great way to think about what this formula here is saying? Well, another great way to think about this, the way I like to think about this formula, is how about we write it like this? A1 is equal to x over a quantity squared plus a y over b quantity squared. Okay, well, if A and B were both just 1 here, this would be x squared plus y squared. Okay, that's if A is equal to B, which is equal to 1. This is just a circle. This is just a circle of radius 1, but when I take this x value and I divide it by a, or I take this y value and divide it by b, what that's going to do is stretch. Thinking in terms of transformations, if I take this x value and I divide it by a, that's actually going to stretch. That's going to stretch the circle in the x direction. Here, this y, when I'm dividing it by b, that's going to stretch. That's going to stretch the unit circle, the circle of radius 1, in the y direction. So when I'm looking at an ellipse and I'm thinking about in terms of transformations, this length from here to here is b, this length from here to here is a. This formula for the ellipse is kind of saying, hey, you're taking a circle of radius 1 and you're just taking the x. You're taking the x direction and you're stretching it by a factor of a. Here, we're taking the y's, we're taking, a circle of radius 1, but what we're doing is we're taking it and we're stretching it in the y direction by b. So that's another great way to see the equation of the ellipse here. Okay. One other thing I want to talk about is just in terms of orientation, Okay, in this case here, we had an ellipse. Here's our foci. Okay, notice it's stretched more in the x direction, and A is what we define as our larger radius. So this will be the equation for an ellipse that's stretched in this direction. But if we flip-flop the x's and y's, if we turn this into 1 is equal to instead a y squared over a squared plus a x squared over b squared, really what we've done is we've just changed x and y, so now we're just reflecting this graph over the line y equals x. We're just flipping the axes. The graph will now be elongated more along the y direction, so it just changes the orientation. Okay, so now these would be our foci. This will be A, and this will be B. So this is how the orientations here would change if we flip-flop the x's and y's. What we're going to do in the last video, I know this one was a lot, but we got there. The work was fruitful. We have our equation of our ellipse. Okay, what we're going to do in the next video is we're going to start working with the ellipse equation. We'll see you there. Take care.